Hello, science students. Welcome to today's lesson about wave interactions. Today, we're going to learn about the different ways that waves react and respond as they come into contact with things like different medium, when they run into each other, or when they travel past different objects. If you think back to our last lesson, you recall that there were specific properties that every wave has. These properties allow us to describe the wave as well as compare one wave to another. These properties included things like the amount of energy that the wave had, the amplitude of its wave, the wavelength or distance between the same spot on a wave, the frequency of the wave, and the speed of the wave. Recall that waves interact with different media and they change. You saw this occur during our wave demo for transverse waves, where we play with the ropes, as well as the longitudinal wave demo when we played with the slinkies. Let's take a look at that slinky demo and focus in as the waves transfer from the right side of the screen to the left. As that wave travels down through the slinky, it collides with the person's hand. That causes the wave to bounce off of the hand and start to move backwards. You can see those areas of compression. They impact and move backwards. Those areas of compression are smaller, so the amplitude has changed. The frequency of those waves also changes, as does the energy that is transferred. Bouncing off of someone's hand and changing directions is just one way that waves can interact or change based on the media. Some of the ways that waves change as they interact include things like being absorbed, being transmitted, reflecting, refracting, diffracting, and scattering. Think back to the last time you heard a loud noise. Depending on how close you were to that sound, it may have been louder or quieter. As that sound wave traveled through the air, some of the energy transfers into the particles of the air itself. Each one of those collisions transfers more and more energy to the air particles, and the wave has less energy. We say that energy from the wave has been absorbed by the air. Absorption is the transfer of energy by a wave to the medium that it travels through. Notice that shows up here as our key vocabulary term. Make sure that you copy down that definition for absorption. It's the transfer of energy. Absorption is the transfer of energy by a wave to the medium it travels through. Some materials are better at absorbing a wave than others. If you think about sound waves, you've probably seen earplugs before. That soft foam material that you plug in your ear helps to absorb a good deal of the energy from the sound wave, and that sound sounds quieter. Or maybe you've seen these neat wave-like bumpy features of foam around areas like a band classroom or a recording studio. These help to deaden the wave and absorb the energy so that those sound waves don't bounce back and forth off of very hard objects. Absorption occurs both with mechanical waves like sound waves, as well as electromagnetic waves like light. We're going to learn more about electromagnetic waves later this week, but all materials absorb those electromagnetic waves. Darker materials absorb more of the energy. And if you think about the differences between like tinted glass and glass that's not tinted, the glass that is tinted absorbs more of the energy of that light than the glass that does not have that darker tint. If you look here at this diagram, you can see that the wave is represented by a line with an arrow, And as it goes from the white medium, or the first medium it's in, it stops as it reaches that gray medium, or that second medium, because the energy of that wave is absorbed. You could also think about a piece of clear plastic wrap and a piece of black construction paper. Light passes through that plastic wrap very easily, but does not pass through that black construction paper. When waves are able to pass through an object, the wave is transmitted. Here you can see 3 different pieces of plastic. One's transparent and you can see straight through. It allows all of that light to pass through. We have that middle one that's translucent and only some of that light passes through. And then you have opaque, where none of that light passes through. It does not allow the energy of the wave to transmit through the medium. Transmission is as simple as the passage of a wave through a medium. Here in our diagram, you can see that the wave is represented by that arrow again. It starts out in the first medium, represented by the white area of the diagram, and it travels right across that border and into and through that gray medium, shown by that arrow continuing to pass through that color change from white to gray. Waves also are able to bounce off of a surface. And you've seen this, like I said, in our slinky waves before, but it can appear some other waves as well. Here we have a video of someone using a signal mirror to bounce light waves in a specific direction. They're using a signal mirror to change the direction of that light wave. You can see the flashes as it lines up with our eyes. Reflection occurs when waves bounce off of a surface. Here in our diagram, you can see that the wave begins to travel through the medium in white. It reaches that border of that different medium in gray, and it bounces off of it and changes direction. You can see that change in direction depicted with that dotted line for reflection. An interesting thing happens. When these waves reflect, they bounce off at an equal angle to the angle that they strike the surface. Straight up and down, a 90-degree angle would bounce it straight back from where it came from. But when you tilt that light, like you see in this flashlight image, that angle from the flashlight to 90 degrees or perpendicular is the exact same angle that it reflects across on the exit path. Here we have an example of a car, and it helps to show these first 3 ways that waves can interact. The glass allows the waves to transmit or pass through the glass. That's why you can see inside of the car. That black paint being very dark, absorbs the energy from the waves. And then those chrome bumpers reflect the light off of them and bounce it back in another direction. That's why you see that shininess of that chrome. Waves sometimes change direction even if they don't bounce off of the substance. Here you can see a light wave interacting between air and water. As that light wave starts to transmit through the water, it gets bent. That light wave slows down. It changes speed. As that speed gets slower and slower, the direction of the wave also changes. And the greater the change in that speed, the more that direction changes, and that more that light gets bent. Refraction is that change in direction of a wave that occurs when the wave changes speed. Here in our diagram for refraction, you can see that the line showing the wave bends or changes direction as it travels through the medium. In this case, it's different than a reflection because it actually still passes through that second medium that's depicted in the gray. Waves don't just change directions when they travel through different media. They can also change directions as they travel past an object. Here you can see some light waves as they are interacting with that rectangular object. You can see that directly behind the object, there's a little area where those light waves are not reaching. But as they move further and further past that object, they start to bend and move and fill in some of that empty space that you can see highlighted here. That can also occur as they pass through an opening. You can see the waves at the top. They're stopped or absorbed by those rectangular blocks, but parts of that wave continue to travel through the middle and the opening. And then as you look at those waves around the other side, you can see that they're starting to spread out. They're starting to get larger. This change in direction of a wave when it travels past the edge or through an opening is called diffraction. Here in our diagram, you can see that you have a wave starting out with the straight line arrow. As that wave passes through the opening, though, you can see that that wave gets bent and changed as it spreads out in all directions there, continuing to travel through that opening. And it shows that with those dotted lines to show how that wave still continues to expand out to the sides, even though a smaller section of it passed through the opening. The final way that waves can interact with different media is called scattering. Sometimes when a wave passes through a medium, it hits a particle. That might be, for instance, a oxygen molecule in the air, or nitrogen molecule in the air, or an actual individual water molecule in water. But as those collisions occur, the wave bounces off the particle in all directions. It's really similar to a reflection, but those angles that it bounces off are unpredictable, and it's sent in multiple directions, not just one direction like a reflection is. Here in our diagram, you can see scattering. As that wave hits that blue particle, you can see that it bounces off in multiple directions. Scattering is responsible for several of the colors we see in the sky, including the blue color of an empty sky, as well as the beautiful colors we get in a sunset. As those light waves interact with the cloud particles and with the particles in the air, different colors are scattered, and we're able to see them because they are sent in paths that reach our eyes. So the blue light scatters in a direction that we can see on a normal cloud-free day. And those reds and pinks and purples that make beautiful sunsets appear as that light gets scattered through the waves.